Welcome to the video on Graphical Behavior 2, Day 4. In this video we're going to continue to explore the relationship between f, f prime, and f double prime. And what we're going to do is primarily focus on understanding what the graphs of them look like overlaid on top of one another. Alright, in example 9 it says if the graph above is the function f of x, what is the open intervals where the function is both decreasing and concave down? So it's important to note that this is the graph of f and not f prime. So we want portions of the graph where we are decreasing. So we're decreasing here and here, as well as concave down. So it looks like the only portion that we are decreasing and concave down is -7 to -5. And also 2 to 3. It's definitely more clear with the 2 to 3 portion that's concave down. I'm going to assume this is concave down and this is concave up. Okay, part B. On what intervals is the function both increasing and concave down? So now we were looking for increasing portions. So this area from -3 to 2 is increasing, as well as 5 to 7. And we want the portion that is increasing and concave down. So this looks like increasing concave up and increasing concave down. So -1 to 2 is the area where we are increasing and concave down. And then finally, where does the graph of f have inflection points? We are concave down to concave up, so we have an inflection point at -5. We also have one at -1 because we go up to down. And then finally, it looks like there's a concave or an inflection point at 3 because we go concave down to concave up. So with 3 inflection points, they occur at the x value of x equals -5, x equals -1, and finally x equals 3. So that's just straight up pre-calculus there, analyzing a graph from the actual function graph itself. As we move on to part B, 9b, they're telling us that the graph is f prime. So we're going to have different analysis if this is f prime. So what we want to do is pursue this under the assumption that the graph is f prime. Where's the function increasing? Well, the function is going to increase whenever the derivative is positive. So our function f is increasing from -7 to -5 because the derivative is positive, and the derivative is also positive from -1 to 7. Since it's equal to 0 at 5, I'm going to break that spot there. So -1 to 5 in union with 5 to 7. At what x values does f of x have a local minima? Well, the local minima for that will occur when f prime changes sign. So f prime changes from positive to negative, and that would be a maximum there because we're going increasing to decreasing. And then we have another sign change right there. We're going decreasing to increasing. So we have a local minima at that point. So let's write that out. F of x has a local min at x equals -1, and then the justification is because f prime changes or goes from negative to positive at that spot. Finally, we're asked, or not finally, but in part C we're asked, on what open intervals is f of x concave up? Since we are given the graph of f prime, what we need to know is when is f prime increasing, because that would mean the second derivative is positive. So f prime is increasing from -3 to 2 and 5 to 7. So write that in here. f of x is concave up on -3 to 2 in union with 5 to 7. And the justification again for that is because f prime of x is increasing. Finally, in part D, it says, at what x values do we have an inflection point or inflection value? So we look at this graph and we're going to look for spots where f prime changes from increasing to decreasing. So at -3, f prime changes, at 2, f prime changes, and at 5, f prime changes. So we have 3 inflection values, and those 3 inflection values are x equals -3, 2, and 5. And the justification for that is f prime of x changes from increasing to decreasing, or vice versa. Okay. And finally, in part C, we're now going to assume that the graph is the second derivative. So if this is a graph of f prime prime, then we know things like when f prime prime is positive, we are concave up, and when f prime prime is negative, we're concave down. So when we go to the question asks us, on what open intervals are we concave down? Well, we're looking for points on the graph where f prime prime is negative. So that occurs from -5 to -1. Since f prime prime is negative, the function is concave down. And then finally, where does an inflection value occur? The inflection value is going to occur where f prime prime changes signs. So there are 2 locations, -5 and -1. And those are the spots where f prime prime changes signs. So x equals -5 and x equals -1. And the justification for that is because the second derivative changes from positive to negative or negative to positive.
I mean next Tuesday. Hey, you there? What? Hey, what? There, there. Hey, hey, you there? There. Hey, there, there. Oh, hey, you there? Okay, I see you over there. One time, I want you to come here. Sit down.
All right, example 10, what we're going to do is we're going to take information and see if we can sketch a graph based off of the information in text form. So let's start here. Sketch possible graph where the first derivative is positive from -1 to, or sorry, negative infinity to 1, and the first derivative is negative from 1 to infinity. So what we know is that up until the value of 1, the function is increasing, and from 1 on, the function is decreasing. The second piece tells us that from looks like we have important things going on at -2 and 2. And we start concave up, and then we are concave down from -2 to 2 and concave up. So what I'm doing is I'm taking this statement and kind of translating it into a very simple representation of what's going on. Finally, our left-hand limit, it approaches, not left-hand limit, but left side end behavior. It approaches -2, and right side end behavior approaches 0. So let's start with the end behavior. Our function is going to approach -2 on the left-hand side, and it's going to approach 0 on the right-hand side. Looks like at 1 we attain a maximum, and at 2 we're going to have a concavity change. So we get concave down to concave up. So that's going on there. And then we also have a concavity change at -2. So we might have something that does concave down and concave up. So there's one possible graph. The y-coordinates of these points can always be, stretched vertically higher, but you want to make sure that you're increasing in concave up to increasing in concave down, and then finally concave down and decreasing and concave up and decreasing. Okay, example 11. In part A of example 11, we are given the graph of the function, and we want to graph the derivative of the function. So what I'm going to do is first I'm going to divide this graph up into portions that have key changes that are happening, and then we'll discuss what's going on in each of those portions. Okay, I drew vertical lines that map out every spot where something in the graph changes, whether it's the slope or the concavity or the sign. And now what I'm going to do is I'm going to think of what f prime would be doing in each of these portions. In other words, is the function increasing or decreasing? So in the first two gaps, the function's decreasing, so our f prime will be negative. Then we have the next two gaps, f prime is positive. The next two gaps, f prime is negative. And in the third gap, or the final gap, sorry, f prime is positive. So we know that the function is going to, or the derivative will be negative in the first two portions. So our function starts negative, and at -3, it's going to transition from being a negative derivative to a positive derivative. And again, that will occur at 2, where it changes from a positive derivative to a negative derivative. And then finally, at 5, we have that going on. So there's a few key points of our derivative. Now we need to think about whether our derivative will be increasing or decreasing. And we take a look at the concavity for that. And in the first interval, our second derivative, the concavity is concave down, so we know that the second derivative is going to be less than 0, which means that f prime will be decreasing. So from -7 to -5, f prime is going to decrease. And then we can do the same thing on the second interval. We are concave up, so f double prime is positive, or you could say that f prime is increasing. And that makes sense because we'd have to increase to get from this point to that point. In the next interval, we look at the concavity, and our concavity is, we're still greater than 0, so that means f prime is going to still be increasing. So we go increasing. Then from -1 to 2, we appear to be concave down. So f double prime is less than 0, which means that f prime is going to be decreasing. So we draw a curve that's decreasing. And assuming this is a vertical tangent line right here, what it looks like is our slope is going to be approaching -infinity. So our derivative basically goes down to -infinity, and our derivative will have a vertical asymptote at this point. Continuing with our slope of -infinity on the other side, you can assume that the derivative does something like this. And it passes through that point at -5 and switches to increasing and positive. So we don't really know what goes on past that point, so we'll stop there. So can we erase that and make it nice and clean looking? Okay, so that red information is the graph of our first derivative. I went ahead and finished filling out the behavior within each segment so that we have all of our second derivative behavior as well as the increasing decreasing of our first behavior, our first derivative. Okay, now we want to graph our second derivative. And our second derivative, we can start by finding the zeros of our second derivative. They're going to occur anytime the second derivative changes sign, except maybe at this vertical asymptote here. So the second derivative goes from negative to positive, so we know there's a 0 right there. You could also think of this as the slope of the derivative is 0 right there. And it looks like we're going to have another 0 there. And I don't think there's any other zeros. The sign of the second derivative does go from negative to positive here, but the function's derivative doesn't exist there, so neither will the second derivative. Okay, and being pretty vague on what we have, we've got the function is going to be, the second derivative is negative, so we are negative down here, and then we go to positive, and the function then is going to, let's see, the slope here goes to negative infinity, so the second derivative will approach negative infinity as well. So we get that going on. And the slope here is positive, so what we need is our second derivative needs to start up high and come down. Stopping somewhere around there. Okay, as it turns out, the more we practice this, we realize that taking our function and going to the derivative it's a slow process that should be done by section, and then going to the second derivative is a little bit harder, but we can take the derivative and treat that the same way to find what the graph of our second derivative is. I personally find it easier to work backwards. If we're given the graph of the derivative, it's fairly straightforward to wind up graphing the function, and that's what we're doing in example 11 part B. So let's see how this works easier. It looks like some of my stuff isn't moving. Let me fix that. Okay, 11 part B. We are given the graph of f prime and we want to graph what f of x might look like. And they tell us that it starts at 0, so I'm going to go and plot on that point right there. And we see that the function is, again, divisible into several portions. I'm just going to call out some important things. If this is the derivative, we see that a local max occurs at this point. So our graph is going to come to a high point there. We see a local min occurs at this point. So our graph is going to come to a low point there. And it looks like our derivative, our slope is, let's see, we get at -3 it switches from being concave down to concave up, because that's where our function changes. The derivative is decreasing to increasing. Continuing on with this curve, we see that at 2 we're going to have a switch between being concave up and concave down. So from 2 to 3 we get this curve that's concave down. That's kind of a sloppy 3. There we go. Looking at this, from 2 to 5 our function is still always decreasing. The derivative is decreasing and positive, which means our function should be increasing but concave down. So we keep our behavior of increasing but concave down all the way out to 5. And then finally, since our function starts to increase from 5 to 7, that means since the derivative is increasing, the function will be concave up. So in that last segment, we want to draw something that's concave up. So drawing one of these off of the other really demonstrates your ability to understand the relationship between f prime and f. And it does take some time to slowly chip our way through all of the important locations where you might find maxes or mins. But more importantly than drawing these graphs one on top of the other is understanding what's going on in each portion. So being able to say, well, I know that from -7 to -5, I know that the function will be increasing because the derivative is positive. Or I know that the function will be concave down because the derivative is decreasing. So that's your primary objective, is to be able to understand that relationship. Okay, so that ends Graphical Behavior 2, Day 4. I know this video was a little bit harder because it really is based on understanding some concepts that are difficult to demonstrate in the drawings. But if you practice developing your key relationships between f and f prime and f double prime, slowly being able to draw these graphs on top of each other should unfold. I know that Khan Academy has some skills dedicated to relating these three, and I would encourage you to check those out to improve your understanding of how these graphs relate. We will also do an activity in class that helps support this understanding. Anyway, thank you for watching and have a good evening.